Okay, hello guys, girls and everything in between. Welcome to the recording of the COMPENG 2D Midterm 1 review. This is a more formalized and scripted version of the same presentation I did about a couple of hours ago, that is last night, 8:30. So a quick word, this is going to be a very lengthy presentation, so there will be timestamps in the description. Feel free to refer to those and skip past whatever you need to know. What I expect you to know for this particular presentation is I expect you to have done at least either attended half the class courses, or attended every lab, or done at least 30% of the homework problems. If you've done any one of these three, you're good. You can keep watching. If you haven't, go do those and then come back. I also want to touch upon the mindset of 2D-F4. A lot of people think this course is really hard because they approach it from the same angle they do 2SH4. This isn't really that. 2D-F4 is more of a logical or digital equivalent of 2CI4, where 2CI4 deals with any sort of current values and any sort of voltage values. 2D-F4 deals with very specific current and voltage values of high and low, true and false. And I'll get more into those later. But I think that if you want to learn 2D-F4 efficiently, make sure you learn the concepts. This entire presentation is going to be very conceptually heavy. I won't be doing all the problems and all the designs and everything. The main reason for that is because if you understand the concepts, you can do all those much easier. It's much more forgiving in that sense than, for example, 2CF4's lengthy problems on determinants and simplifications, or 2SH4's lengthy algorithms that you have to write for pointers and things like that. And finally, a quick personal message. If you did enjoy this and if it did help you get a better grade, please feel free to drop a few dollars on my Ko-fi. The link is on the screen right now over here, and on this QR code right here. Of course, you are not obligated to do this, but I do appreciate it. I did stay up a long time for doing this, and it's gone through a lot of revisions, so I hope you enjoy it. Right, with that said, let's move on to the course checklist. So I'll be covering everything here. This is everything you need to know to basically ace this course. If you can tick off every box over here, you will ace this course, definitely. But I will not be covering week 4, mainly because I'm not good at Verilog and VHDL and any of that stuff. So I would suggest you consult someone smarter than that to revise this topic, because I am definitely not that person. So yeah, week 4 Verilog and VHDL is off the table for now. Moving on, I'm going to get started with number systems. So this is a pretty difficult topic, and my presentation is going to be very heavily weighted towards week 1 and week 2, mainly because I think the professors rushed through this a bit too fast, which kind of caused a few confusions on the later parts of this course, like synchronous logic and some of the combinational circuits. So I'm going to try and be very thorough with this and make sure you guys understand it. So first off, what I want to make sure and emphasize is that the decimal system that we use is completely arbitrary. This system is not really, like, using 9 digits 0 to 9 is completely random and made up. Like, we could have lived our entire lives using a 8 digit system, or a 3-digit system, or even a binary system, or a 25-digit system, and it would have worked just as fine. It's just that because you've learned from your formative years that we use decimal system has become the only acceptable alternative for you. However, this isn't true. You can do every math you do in decimal in any other system. It just so happens that the one we used happens to have 10 symbols, and we call it the decimal system. So don't think of the decimal system as the default, think of it as one of the options. And this is something I really want to emphasize, because a lot of people get confused with number systems. The main thing I realize is the decimal system is not the default. So here I want to present a decimal number as something you've done in 3rd grade, place values of a number. This is usually called the face value of a number. And you've also learned how to convert this to the place value of a number by multiplying each digit, each symbol, with its place 10 to the power of the place, as seen there. And this gets kind of important as we go on to more other number systems. But what I want to emphasize is the reason we use 10 here is because that is the base of our number system. It is a base 10 system. So 4 2069.346 gets decomposed to 4 times 10 to the power 4, 2 times 10 to the power 3, 2, 1, 0, and then after the decimal point it's negative numbers, so negative 1, negative 2, negative 3. So, as I said, the decimal system having 10 digits is completely arbitrary. Let's try making our own system, just to get a feel of how arbitrary the decimal system actually is. I'm going to make a random one called base 6 with a twist. Instead of using 0 to 9, which is just random squiggles on a screen, like 0, 1, 2, all these are literally just random squiggles on a screen, I'm going to use other random squiggles on a screen, P, Q, R, S, T, and U to denote our digits. There are 6 of them, and this also means that imagine you're an alien who grew up using base 6. To you, this would be the normal system. And when you talk to a human, you would have to convert your base 6, into the human base 10. And to do that, we would use the decimal value expansion. So QTU.R is a number in your usage. You know that this is a number, and this is a perfectly valid number. However, it doesn't translate to base 10. So to translate it to base 10, you would tell the human to put this into their calculator. So the symbol, as mentioned above, it's the same analogy over here. Q times 6 squared, T times 6 to the power 1, U times 6 to the power 0, R times 6 to the power minus 1, and all of these together form the decimal equivalent of the number you're supposed to be using. So if the human put this into their calculator, it would give them a decimal answer. However, if you put this into your calculator, it'll probably give you a base 6 answer. That's again because being the most common system, decimal system is used in calculators worldwide. So when you put in an answer, you get an answer back in base 10. But when you put in a calculator in let's say binary, you'll get an answer of base 2, and so on. So let's talk more about the base 6 system, and just to get an intuition for how bases work. Imagine counting in base 6. So just like you count in decimal, an alien would learn to count starting from the equivalent of 0, P. So they'd go P, Q, R, S, T, U. And once they run out of letters, just like when you reach 9, when they reach the equivalent of 6, which is U, when they reach the equivalent of 5, which is U, they will just move 1 over. So QP, just like it's 1, 0 for decimal, it's QP for base 6. QQ, QR, QS, QT, QU, RP, RQ, RR, RS, RT, RU, and again you've reached the end, loop over, one more, add 1 to the add a Q to R to get S, and then it becomes SP, SQ, SR, SS, and so on up to the random number I picked, QP. But what's important is, just because you're using this number system, there is still other number systems you can use. So here is the decimal equivalence of the first row of number systems. So this is all of these numbers represented in decimal. So if I told somebody I had S things in my box, I know I have this things. They would call this 3 things. Similarly, if I told someone I had QT things, I would have these many things, which they would call 10 things. So they count the same quantity, just represented in different symbols. So here is more of these. You can pause here and have a look and make sure you understand this well. If you want, rewind and try and make your own one. So try and make this list on your own and see if you understand it. Now, what if I do what we do with most other number systems? Instead of using random symbols, we use the same symbols we've used for decimal in other number systems. So I again want to emphasize, 0 here or 1 here or 2 here does not mean 2 decimal. It means 2 base 6. And the fact that we use 2 in both of these, that's what gets people confused. We could use anything. We could use Greek letters, we could use shapes, but we try to use the same symbol. So remember, this is just a symbol, it doesn't have the same value. So once again, when we reach this is not a 10 decimal. This is 1, 0 base 6, which is actually 6 base 10. So this can get people confused a bit. Again, I want to emphasize, try this out yourself. Once you reach 5, you have no digits to go to. So you put a 1 and then you put a 0. Similarly, how when you reach 9, you have nowhere to go to, so you put down a 0 and then you add a 1 to the tens place. In this case, we'd probably call it the 6's place or whatever. So yeah, Moving on, you'd count up to 1 1, 1 2, 1 3, 1 4, 1 5, run out of digits again, increment the 6's place to 2 0, 2 1, 2 2, and again, none of these are actually 20, 21, and 22. In fact, they're 12, 13, and 14. And so on up until you reach decimal 30, base 6, 5 0. This can keep going for infinite number of symbols. You can keep adding stuff, and just like how you can pad zeros to a decimal number, you can pad zeros, quote unquote, to your base 6 number. Now a more 2D effort look on everything. So now that you know all of this, let's look at actual number systems that you'll be using often. A term you got to know is the radix. The radix of a number system is the base of that number system. That is, how many symbols do you work with? It's signified by the letter R. The most common one is, of course, base 10. You already know this one. It has a radix of 10, which means it has 10 symbols right here. Again, like I said, these symbols are just random squiggles on a page. Don't think of them as specific numbers or something special. You could replace all these with whatever you want. So someone out there could be using a base 10 system which uses letters instead of numbers, or it uses I don't know, every single BTS member. But yeah, the decimal equivalence, which is the stuff you type into a calculator to get the decimal version of a decimal number, is symbol times 10 to the power place. And you add these up and you get the decimal equivalence of the number. Moving on, you might have a more common system, binary. Binary has a radix of 2 because it has only two symbols, 0 and 1. Again, I could use any other symbols for this. The decimal equivalence, that is what you type into a calculator to get a binary to a decimal, is the symbol times 2 to the power place. So if I have a binary number 1 0 1, I will type in 1 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1 times 2 to the power 0. And when I add this up on my decimal calculator, I will get a decimal number. There's also octal and hexadecimal. These two are usually used to represent binary. Because their bases, their radixes are a power of 2. They use and the decimal equivalents are equivalently similar. A quick note on hexadecimal: since hexadecimal has more digits, more symbols than decimal, we have an extra set of symbols, A to F, to represent the extra digits. So like I said, this could have been anything. I could have made A, B, C, D, E, F here, and these could be called G, H, I, J, and so on. But we just choose to use A, B, C, D for the extra digits that we don't have. Similarly to an alien who is using base 6, the 7, 8, 9, and the symbols that we have here will look as bizarre as A, B, C, D, E, F look to us. A quick bonus: in this course, you're only supposed to know how to convert things to decimal. However, you can also learn how to convert decimal to anything. It's not very hard. All you have to do is put down the number and repeatedly divide by the radix of the base you're trying to target, and keep track of the remainder. So the modulus operator, as you might think of it, the remainder of the division. And read this, once you finish it and reach a 0, read this bottom to top. So I reach a 0, I read this bottom to top. I reach a 0, I read this bottom to top. And this gives me the base equivalent of that number. Why is this useful? You'll see in a moment. So yeah, this is not in scope, but you might want to learn it anyways. Another thing about number systems is that we usually use binary from now on, and binary is a very interesting number system. It has a lot of detail on how it works, and importantly, we can binary is usually stored in computers, and in computers, data is a constant stream, so there's no breaks, there's no extra symbols. It is literally just ones and zeros. So how do you put if I know the how do I use negative numbers in a system like this? Well, the simple answer is define your number to be a certain size, usually say 8 bits. So I define my number to be 8 bits long. In, for example, modern computers, we might have numbers that are 4 bytes or 32 bits long. So they allow for much bigger numbers, but yeah. So now these are two separate numbers. Your computer knows that these are two separate numbers because it fixed the length. But how does it know the sign of these numbers? Well, there is two ways to do this. Number one is allocate the first digit to the sign and the rest of the digits to the magnitude. So for example, if I wanted to represent -7, I could represent it as the magnitude, which is 7 digits. So 0, 0, 0, 0, 1, 1, 1. And then I put a sign. The sign will be 1 for a negative sign and 0 for a positive sign. So here is a negative sign, so I'll put a 1. That is the sign and magnitude representation. This is very easy to understand while reading because all you have to do is find the next 8-bit block, take the first digit out, look at the rest, and then that's the magnitude and the first one is sign. However, this is nearly impossible to do math with. So we figured out a different way to represent negative numbers. We figured out that we can represent negative numbers as radix complements of a positive number. Why is this important? Well, a radix complement is a function such that a plus f of b, f being the radix complement of b, so a plus the radix complement of b actually gives you a minus b. So you can subtract two numbers by adding the radix complement to the subtractand. And this is useful because computers can add better than they can subtract. So we can just get a computer to add the radix complement of a number to the number that we're supposed to be subtracting from. How do you find the radix complement? What is f of x? Well, f of x for any number, not necessarily binary, n with a base of r, a radix of r, will be the radix. So r to the power n minus n, the actual number. And n here is the small n is the number of digits. Examples over here are given. So the radix complement of 52520 over here in base 10 is the base to the power number of digits 5 minus the actual number, which is this. Similarly, this is another binary number 0.3267. There are only 0 digits here, so there's nothing before the decimal point. So 10 to the power 0 minus 0.3267 is equal to 0.6733. More importantly, you'll have to deal with 2's complement, that is base 2 radix complements. I assume you guys also know the trick where if you have a 1's complement, you can add 1 to it to get the 2's complement. Right. So this is the same, this is the actual method of doing it, this is the shortcut method. And this only works for numbers that don't have a binary fractional component. So they don't have a fractional part after the decimal point, or the binary point, they only have a whole number over here. So why did we go over this? Well, again, a radix complement is a function such as m of m minus n is equal to m plus f of n. Now you already know how to add binary numbers. You already know how to do this. It's basically literally the same addition that we've done in primary school, except now you can't write 2 anytime you reach a 2. Just like you reach a 10, you carry 1 and then you keep writing the number. So how does this work? Well, to subtract two numbers, we just use the same addition technique, but we use the radix complement, f of n. So add m to the complement of n, see if there's an extra digit. If yes, your answer is positive. Discard the end digit and report your answer. If no extra digit, your answer itself is negative. So let's go over that with an example. 12 base 10 minus 15 base 10. Usually you won't be given these decimal numbers, you'll just be given the binary equivalents, but you can sometimes convert it to a decimal number to check if your answer was correct. So you'll just be given this in a question. So now I need to subtract 1111 from 1100. How do I do that? Well, I can't subtract, I'll just add the complement. And the complement is 0001. You want proof of that? It's basically the bit switch of this. So the 1's complement added 1, so 0001. Put this back here. And now I add these two numbers, I get 1101 base 2. Here's something important. How do you know whether this number itself is a negative result or a positive result? Simple. You check if there was an extra digit when you added these. So I start off with 4 digits here, I start off with 4 digits here. The bigger number of digits, that's what you consider. Here the bigger number of digits, they're both the same number of digits, so they're both 4, but the answer is also 4 digits. So your answer itself is actually negative and is in the form of a radix complement. So the answer is negative. Let's report it as the negative of its actual value. So the radix complement of a radix complement is equal to the number itself. So I know this is a radix complement. Let's take the radix complement of the radix complement. So 1101 bit switched is 0010. And then I add 1 to it, 0011. 0011 base 2 is 3 base 10. I put a negative sign because I just complemented it. So the math checks out. 12 minus 15 is 3 in base 10. Again, now if you had got this answer, you can always double check by doing it in decimal and then converting this back to binary and converting these back to decimal. you'll get these in binary. So that's why I put that bonus slide in so that you can check your answers when you're doing a sum like this. It's very easy. Okay, so what's the point of doing number systems? What's the point of doing binary? Well, interestingly, it's all because of this guy, George Boole, wonderful dude, number one, A plus, Boolean continuously. He figured out that we can have a branch of math where we can do math on logic, that is, things that work on true and false. Usually when we think of a variable x, we think of it belonging to a certain domain, like integers, or reals, or complex numbers, or I don't know, quaternions, whatever you prefer. But in Boolean logic, a variable can only have two values, 0 and 1. Discrete values that aren't, there is nothing in between them. Sorry, I shouldn't be using that symbol, then it's probably easier to use this. There we go. He also figured out that just like you can do operators on regular variables with regular math that belong in these domains, you can do operators with these variables, and he called these Boolean operators. I'm not going to go over these. I assume that if you've attended at least a single 2DFO lecture, you probably know what all these are. So yeah, just these the operators, and that's how they work. This is the logic behind why we learn binary and what it all means. And this is important. Why? Because I'll let you know in a bit. So Boolean algebra is a field of algebra developed by George Boole to do math on Boolean values. And just like in math, when you have a function y is equal to f of x, or you have a function k is equal to f of x comma y, you can figure out the value of k based on the values of x and y. Similarly, you can have a function f of x, y, z, which depends on Boolean variables and Boolean operators. So this is similar to how you would write k is equal to x squared plus y squared. This is also x and y or not z. So these are all operators, just like square, square, and plus are operators. Obviously, just like how we have rules for regular math, there's rules for Boolean math. These are all the rules for Boolean math. I won't be going over them. It's easier to do these with an example, and I'll be doing an example later. But I would encourage you to look at these. These are all given in the paper. So these will come with your exam paper. You can have a look at these anytime. So let's also talk about truth tables. But before we do that, let's try and look at this particular Boolean expression. So this is a function given to us, h as the output, a, b, c as the inputs. You'll notice there is no c here. It's like kind of, it's supposed to be there, but well, there is no, it's not dependent on c. So let's try and simplify this. We know that b plus b complement is a Boolean 1, and a b plus b complement can be simplified to a b plus b complement. And this again is the same as the previous line, which is also 1. So this becomes 1, a, 1, 1 and a and 1, which is a, if you look back at these rules. So the h is actually a after simplification. So this is similar to how if I gave you a function in real numbers, f of x is equal to 2x plus 3x, you will write this, you will simplify this instantly as 5x. So similarly, you can use these rules, special rules, to simplify Boolean expressions. Now, in a regular function, we draw graphs to represent every single value of a function. So for every value of x and y, what is the value of f? Well, we usually draw out maybe something like this. So x, y, and f. So I can draw out the graph for x and y, and then for any given x and y, I can find the value of f. However, in Boolean systems, there's a special property. Since every variable can only have two states, 0 and 1, you can just write down every single possible value of a Boolean variable and figure out all the combinations. So this is very important. You need to cover every single combination. How do you cover every single combination? Well, look at a, b, c as a base 2 binary number and start counting in binary. So this, if you look at decimal equivalents, this will be 0, 0, 0, which is actually base 0 base 10. This is 0, 0, 1, which is 1 decimal. This is 0, 1, 0, which is 2 decimal, 3 decimal, 4, 5, 6, 7. And if you count up in binary, you will actually cover every combination of A, B, and C possible. So mathematically. And then we write down the values of h for all these. Well, how do you find the values of h? Look at the expression. H is equal to a. So h will be every value of a for every combination of a, b, and c. So h is just a. Okay, why do we do all this? What's the point of building this field of mathematics of Boolean algebra? Well, it's pretty simple. We figured out that, well, we didn't figure it out. It was well, I forgot the wonderful gentleman's name who figured this out, but there was somebody who figured out that these systems can be represented by an electrical system where we have a high depending on one voltage, like V1, and we have a low depending on another voltage, V2. Now any components in the system can read the voltages and work logic on them. So as we build things, we can have components read each other and interact with each other. Depending on so how do we know what V1 and V2 are? Well, it depends on the architecture. So depending on the standard you follow and the components you've bought, they follow one of two architectures, CMOS and TTL. Obviously, don't mix components, don't mix standards. That wouldn't make much sense. So in CMOS, true values are represented by anything from 2.0 to 3.3 volts across a component, and false is 0 to 0.8 volts across a component. Similarly, in TTL, the input true is 2 to 5 volts, the output true is 2.7 to 5 volts, and falses are the same for both these. So anytime the component reads any voltage, it compares it with what it knows. As you notice, there's a gap between T, the upper and lower ranges, and F, the upper and lower ranges. This gap is on purpose. It's to make sure that any value here is counted as an error, not as true or false. So the component won't do anything. Like, it won't really regard any logic out of this. So that means the previous analysis failed, or you have a bad electrical component. So that covers week 1, everything you need to know. Moving on to week 2, Minterms and Maxterms. So on a truth table, you can get value of h. And what you can also do is get a special case such that, what if you have only one h equal to 1? You only have one of these. Well, in that case, someone figured out that you can just write the function of h as a minterm of the inputs a, b, and c. And whatever the value of h is, you write down a, b, c, and you complement if the value of a, b, and c at those points is 0. So let's say for here, we notice that h is, if this was the only one, so all of these were actually zeros, h would be equal to the minterm at this point. The minterm at this point is ABC with complements wherever there's 0. So A, B complement, C complement. So h would be equal to A, B complement, C complement. If there is more than one h equal to 1, then h is the sum of these minterms. And similarly, someone figured out that for if there's only one h equal to 0, then you can use the corresponding max term. And if there is more than one, then you can use the product of the max terms. So we usually represent products by pi of the max terms. So all the max terms. As you'll notice here, I've written down all the minterms and the max terms. How do you generate a minterm? As I mentioned, it is you just write ABC as an AND operator and complement the ones complement wherever there's a 0. And for max terms, you use an OR operator and complement wherever there's a 1. So again, remember, these are kind of the yin and yang. The minterms are for values equal to 1. They are AND operators and they complement for 0. The max terms are 0 values. They are OR operators and they complement wherever the inputs are A1. So as you notice, here nothing is complemented. Here the C is complemented. Here the B is complemented, and so on. So as mentioned, you can represent a function as a sum of minterms or a product of max terms. These are both very important representations. These are called SOP and this is called POS. It is called POS because it is a piece of shit to simplify, but yeah, we work with what we have. As you will notice something interesting though, the minterms and the max terms of a expression will always be complementary to each other and they will always cover the entire function. This is kind of obvious because if it's not a 1, it's a 0. Like, thank you, Yash. But you'd be surprised how many people don't figure this out. So if you're given the sum of minterms, to get the product of sum, just do pi of 0, 1, 2, 3, and you will know this is the product of sum. Just easy conversion. This way of writing down the SOP is called the standard form. And this way of writing it is called the canonical form. So sometimes you'll be given the canonical form just to make things simple. Obviously, you can derive the standard form from the canonical form and vice versa. And once you get the standard form, you can use the Boolean like theorems to simplify this and make it a simpler function. You don't need to do this, but you can if you want to. And yep, usually we represent minterms with a small m and max terms with the capital M. And obviously the number after it refers to the decimal equivalent of the combination of A, B, C on a truth table. The same thing I went over just before. This is important. Using De Morgan's theorem to invert SOP and POS. So if you get a canonical SOP like this, you know that it was 1 at 1, 4, and 7. And that means if you try and do F complement, you know that the result will be 0 at these points. So now F complement will be equal to pi of 1, 4, 7, or the SOP of 0, 2, 3, 5, 6. However, these both are equivalent, obviously. They're therefore the same expression. They just are expressed in different ways. However, importantly, this is the derivation for the exact process. And also you can double complement this to get back the F, but in terms of the parameter sums. So yeah. So that covers Boolean expressions and simplifications. Let's move on to a more easy simplification. But Yash, I don't like to use Boolean theorems, you say. No problem, someone else beat you to the punch. Karnaugh maps were developed to minimize an expression without Boolean algebra. All you need is a truth table. How is this actually helpful? Well, in some cases you might get a design problem. Say you are given a system which has a bunch of data points. The data points are the temperature in your house um, is above 20 degrees, the humidity in your house is above 80%, and the like I don't know, the outside time the current time is after 5 p.m. All of these can have true or false values, and this becomes a logic problem. So if you have a humidifier, you want it to be on for this being 1, but you also want to save power, so you want it to be on for also this being 1, and oh sorry, a dehumidifier. Let's say you have a dehumidifier, you want this to be on for this being 1, and you want this, and you want to save power, so you don't want to run it before 5 p.m. So you also want this to be 1, but you also you don't care about this. So you might get, if you want to design this, you would have to make a truth table for all values of this, this, and this, and then you would get a result. So you could get the minterms and simplify the truth table with that, but there's a simpler way. Use a k-map. A k-map can be of different sizes, and here I'll be showing the 4-variable k-map. This goes from, so this is a function w, x, y, z. And to build a k-map, you make a blank k-map first. This is a blank k-map, and we start off by writing down wx on one side and yz on the other side. Then we write down the possible combinations of wx and yz on the rows and columns. So yz could be 0, 0, so y0, z0, 0, 1, 1, 0, and 1, 1. Notice how I flipped these positions. This is because of a feature called gray coding. You can learn more about that if you want to, but you don't need to. All you need to know is that these are flipped positions as you would normally count in binary. So make sure you remember this, otherwise your k-map will not work. Similarly, we do the same for wx, w equal to 0, x equal to 0, w equal to 0, x equal to 1, w equal to 1, x equal to 1, and w equal to 1, x equal to 0. Finally, we write down the addresses, sort of the table cell numbers of all of these. And to find the table cell number, all you have to do is read this as a binary number, like left to right. So 0, 0, 0, 0 is 0, and oh sorry, one second. I'm just going to clear that up to make some space for myself. So yeah, 0, 0, 0, 0 is 0, so this is now M0. Let's pick another one, 0, 0, 1, 1. For this cell is 3, so this is binary 3, so this is cell 3. Let's pick another one. How about this cell? 1, 1, 1, 0. Well, this is binary 14, so this is going to be M14 in decimal, so this is. And 1, 0, let's try this cell, 1, 0, 0, 1. So this is binary 9, so this is M9. You can fill in the entire cell like this, and now you have the entire blank k-map. Next, you will look at the truth table given to you. So this is a random truth table I pulled from the internet. I have no idea what it actually does, but yep, someone must have designed this, and yeah, now we can use it. So to design the truth table, all you have to do is fill in the blanks. We know the cell addresses, and wherever there's a 1, you put down a 1. The other cells can be blank, or you can put them as zeros. There is a special case where you don't put a 0. We'll talk about that in a bit. So this is a truth table with a random selection of maps. And here the ones are only for the M1, M3, M7, M15, and M11. Great. So when I fill these in, this is what I get. But now how do I work with this? Well, I have to group these. The grouping rules say that they're the same property as the Boolean expression simplifications, where if you have two complements, this becomes 1. If you multiply two complements, this becomes 0. So this uses the same property of that, just in a more mapped out way. So if you look at this, these elements, this one and this one, are actually differing by a y and y complement. So if I took this element out and I added them up, it would get w complement x complement z y complement plus y. And this will become 1, so this will be left with w complement x complement z. So we simplify the expression. This gives you a hint as to how you're supposed to make these groups. Groups work on adjacents, which are powers of 2, and, sorry, not n to the power 2, 2 to the power n, and they work on adjacent cells. So I can make this a group, and I can make this a group. Let's call this group G1. Let's call this group G2. Now, these groups will then form the elements, and once we figure out their elements, so for example, I explained to you how to find G1's equivalent. Now you can find G2's equivalent by looking at what doesn't change in the group that we've made. So M3, 5, 7, 11. What doesn't change is YZ, so that is YZ. We add, and the actual function is then given by the sum of these groups. This is mathematically simplified. This means that there is no way to get this any simpler. There is no like trick or method that you can use to make this any simpler than it already is. Moving on. You can also have certain cases where you just don't care about what the output is. This happens more than often than not. So for example, I mentioned about the this example over here. What if you don't care about what the outside temperature is? It could be 0 or 1. In that case, anywhere there is a difference where only the outside temperature is the difference, you could just put down I don't care about what f is going to be, and you represent a don't care with an x. So if you have a don't care in a truth table, it's important to know how to work with it. You can choose to include it if it simplifies your inclusion, if you can make a bigger group, because as you know, a bigger group eliminates more variables. But if you choose to not use a don't care, well, you don't need to use a don't care. It doesn't matter. You don't care whether it's used or not. So here we have the same function, but we add some don't cares. Also, I should have probably made this a 5. It's not a 15. But how this would work is, if now the groups I can make look something like this and this. I included these two x's because they make my group bigger, which means I'll get a better simplification. And similarly over here, I'm not including this because I don't need to. I don't care if it's included or not. Another way I could have simplified this is, so I could have x, 1, 1, x, 1, 1, 1. I've made the first simplification over there on the right side, but I can also make this simplification, which again, the rule is you have to include every single one in the table, but you don't need to include every single x. This is the same. This is going to give you a slightly different result as a function, but it'll perform the exact same function, like the same job. It'll give you the same outputs of 1 for where the inputs are a certain value. Again, I don't include these two x's because I don't care about them. So a few important terms. Implicants are what we've been using as groups. You can make an implicant of any size. I can make an implicant of 2 elements, but usually we work with prime implicants. Implicants which have the maximum size possible. So this wouldn't be a prime implicant because it only takes up 2 cells when I could make an implicant of 4 cells including it. So this would be a prime implicant. The bigger one would be a prime implicant. So also we work with essential prime implicants. A prime implicant which you need to have to cover one of the midterms. So over here, these two are prime implicants, and over here, this one and this one are prime implicants. However, if I now made a box over here, this would be a prime implicant, but it would not be an essential prime implicant because every other one is already covered, and all I'm doing is adding an extra x, which I don't care about. So me making this does not make the equation any simpler. In fact, it's just probably complicated even more. A quick footnote, 5 variable maps. Why are we not going over 5 variable maps? I don't think they will come. Right. because they just take up too much time. I doubt they ever put this on an examination paper. It's just simply unnecessary. Though if they do put it, then I've jinxed it. So you're welcome for giving you a free 10 marks. Just go ahead and learn it because I've said it's not going to come. Okay, that covers the entirety of week 2. Moving on to week 3. Let's talk about combinational logic. Combinational logic is a field again that I think they didn't touch upon well because they didn't touch upon the first 2 weeks well. So when you talk about decoders, encoders, multiplexers, adders, all of these are fancy terms for just basically what is a chip. A chip that can do the exact same thing over and over again. These are things you would encounter in the industry because they are commonly used functions. So think of this as Pokemon. They have properties, and you should know their Pokédex entries to be able to use them in the actual job world. So a decoder is a device that can take a binary number as an input and turn on that corresponding numbered output. So this is important. Understand this. A binary number, right, is an actual number. The numbered output is an output that has a memory address sort of associated with it that will only be turned on when that particular address is entered in binary. So if you want a better analogy, think of it as a bouncer as a club. It will only open the door which you're allowed access to. So if you are a guy who is under the age of 18, you will only be allowed in the under 18 guys group. There will probably be an over 18 guys. There'll probably be a under 18 girls. There'll probably be an over 18 girls. There'll probably be an under 18 everyone else, so non-binaries or whatever, and there'll also be an over 18 NBs, pans, transsexuals, whatever. And depending on the door you wish to go to, the bouncer, this man over here, and his politics will decide which door you go into. So yeah, importantly, now that you know all this, try and come up with it yourself. Pause the video now and try and make your own decoder. Remember, you already know exactly what it's supposed to do. All you have to do is design it. So let's go over how you would approach this problem. What do we need? We need, for any number of binary inputs n, it should turn on one of 2 to the power n binary outputs. So only one of these should be on at a time. But how do we achieve this? Well, what gate do we know that can be on for only one combination of inputs? The AND gate. The AND gate is only on for one combination of inputs, which is 1, 1, 1, 1, all ones. It will only output 1 for that. So all we have to do is create an AND gate, where the inputs to that AND gate are the particular binary number converted to ones. So take a look at this output sheet over here. Here we have 8 outputs for 3 binary inputs. So for 3 binary outputs, 2 to the power 3 binary outputs. We need D0 to be 1 and all the others to be 0 for binary input 0, 0, 0. So simple. Put a complement after all of these. This will give you 1, 1, 1, which means only this will be on for this one and all these will be off. So I wire up my 1, 1, 1. So this is Z complement, this is Y complement, this is X complement, and this will give me D0. Similarly, let's pick another one. Let's pick D3. In D3, I need a 1 when the input is 0, 1, 1. So here, these are already 1s. I need this complemented. So D3, again, I will just write, if I follow these lines, you will see this one comes from here. And this one is a line that goes to the X complement, and this one goes to the Y complement, and this one goes to the Z complement. This one goes to Y, and this one goes to Z. So X complement, Y, Z. Simple. So yeah, please don't try and memorize this entire diagram. Just derive it yourself. You will never be able to memorize such a weird and annoying diagram. Okay, so for every decoder, there must be an encoder. For every Jedi, there is a Sith, or so the legends told. For any one of 2 to the power n numbered input lines, generate the corresponding binary number and output it through n output lines. Exactly the inverse of what we did here. This one's a bit harder to design, but the easiest way to just make an observation using the truth table. If you stare at this, you know exactly what it's supposed to achieve, literally the inverse. But if you stare at this hard enough, you will notice that Z is 1 for every odd number D of 1. So D equal to 1, D equal to 3, D equal to 5, D equal to 7. And you might think, well, I know only one of these can be on at a time. So if I just use an OR gate, and I or D1, D3, D5, D7, then when any of these one of these is on, I know that Z will be 1. Well, mission accomplished. Similarly, you can figure this out for Y and for X. And once we do that, we can achieve this. This is a circuit of the particular one. So if you notice on Y0, which is what we would normally call Z, it is connected to D1, D3, D5, and D7. So it's only 1 for these values. Similarly, here this one's connected to D2, D3, D6, and D7, as specified by the truth table over here, and so on. Okay, so moving on to the next device, the multiplexer. The multiplexer is a bit more tricky. This one's a routing switch, essentially. It allows you to navigate traffic going in from multiple lanes. So again, going back to the bouncer at a club analogy, you have a whole queue of people lining up. You can only let in one person at a time. So you will let them in maybe first from the first row, then you let one from the third row, then you let one from the second row, then so on and so forth. Remember that you're not necessarily letting in a value of 1, you're letting in an input. The input could be either 0 or 1. So what I need is that I need a way to get y equal to d0 when I flip a switch. I need a way to get y equal to d1 when I flip a switch. I need a way to get y equal to d2 when I flip a switch, and so on. And the way I flip the switch is using select lines. So the select lines act as a binary number, S0, S1, a binary number. So it could be 0, 0, 0, 1, 1, 0, 1, 1. And whenever I have 0, 0, I want D0 to flow through it. When I have 0, 1, I want D1 to flow through it. 1, 0, I want D2, and 1, 1, I want D3, so on. So basically, I'm trying to decode the select lines using AND gates, similar to how I've done in a decoder, and then feed them in with input lines. So this is how it would look. The circuit's given here. So again, D0 will become the output only when S1 is low and S0 is low, that is their complements are high, enabling this AND gate to pass D0. So if D0 is 1, AND will be 1, if D0 is 0, AND will be 0. And all the others won't work because their select line values are not high right now. So no matter what happens to D1, D2, D3, just because S1 and S0 are 0, these won't be able to go through and only D0 will. So yeah. Moving on to the half adder. The half adder is a pretty simple circuit. It is a way to add two numbers. It adds two binary inputs, gives us some output and a carry out. So you already know the circuit for this. S is equal to A XOR B. Carry out is equal to A and B. Very, very, very importantly, for all combinational logic circuits, they have no idea what purpose they're accomplishing. Okay, an electrical component is not smart. These things have no idea what they're doing. All they know is that they're supposed to get a truth table of outputs. So you can simulate addition by knowing how addition works. You can have numbers add up, and when you run the sum table, you realize it becomes 0, 1, 1, 0. And this, if you realize, looks like an XOR gate. So you just put an XOR gate for sum. It doesn't know, this XOR gate doesn't know it's adding two numbers and giving you the sum digit of this particular addition. It just knows that it's, well, it exists and it's processing some two signals, low and high. And the same goes for any of these. Whenever you design these, they don't know they're selecting a digit. They don't know they're doing any of that. They just are following a truth table. So the main thing you need to remember is the truth table is king in Boolean algebra. This is called a half adder, as I mentioned, and it adds two binary inputs. However, this is kind of useless. Moving on to the full adder, the cooler one. Why should you use a full adder? Well, it's simple. You can link multiple adders together to add more numbers on top. And the reason for this is because a full adder can add 3 binary inputs and also give you a sum and a carry out. So why is this important? Simple. Here is a full adder taking in a value, say A and B, and a carry C in. And this will give me a sum out and a carry out. But what I can also do now is wire these to another full adder and add another number to it, D. This will give me another sum and carry out, which then I can wire to another full adder and add a number E to it. This allows me to chain full adders to make any number of adders, and that's why full adders are so useful. And the only reason they can do this is because they have 3 binary inputs. Not much has changed from the previous one. As I mentioned, a full adder is a collection of half adders. So Importantly, please make sure you write C in and C out. You don't need to use these particular variables, but if you're writing C for both of them, make sure you write one of them as in and one of them as out. I have lost marks for this before. So how do you design a full adder? Well, a full adder is two half adders. Half adder is A XOR B. A full adder is A XOR B XOR C. A full adder is carries out is A and B. A full adder is carry out is A and B and C. And the circuit is pretty self-explanatory. Here you go. Okay, that concludes every single possible logical component. A quick aside to that one numpad question. This question is frankly appalling, but it is a very clever question, and a lot of people have had trouble with this. My advice to you is, I won't teach this. The simple reason is it doesn't work. You cannot be taught this question. This question is a design question, and that's what it should be. You should try and design it yourself. I learned this in Dr. Bowman's class. I took notes, I paid attention for that lecture, and I still didn't understand it. I went back home, I cracked my head against it, I failed about 4 times, but then the 5th try, I got it right, and I understood the entire system. So the best way to learn design questions is don't read someone's explanation and assume you've understood it. You will forget it. Read someone's explanation and then try and compose it yourself in your own way. Don't use the same symbols. Try and use different symbols. Try and use a bigger numpad. Try and use a small numpad. Can you get the same results? So yeah, I think that's the best way to approach this. Okay, so that concludes week 3. A quick break for anyone who is still, watching and is not asleep by now. We will start with week 5. As I mentioned, I won't be covering week 4 in a little bit. So go ahead, take a stretch, pause the video, and leave a like. I don't know. I'm not really good at this YouTube stuff.